1.5, we've actually taken a look at pieces of this already. So some of this is sort of putting to pen and paper what we've verbally said aloud. This is talking about limits involving infinity. So remember this basic function 1 over x. You guys know what it looks like, right? I used it as an example last class period, and I sketched a very rough estimate of it looking something like this. That second one was pretty smooth. We talk about this graph having 2 asymptotes. One's a vertical asymptote, the other's a horizontal asymptote. So the vertical asymptote, I'll draw it in, is right here along the y-axis, right? And that vertical asymptote has an equation. It's called x equals 0. Because everywhere along the y-axis, x is equal to 0. And then I have a horizontal asymptote. It's right here. It's the horizontal axis, the x-axis. And everywhere along the x-axis, I have the equation y equals 0. So my horizontal asymptote here is actually y equal to 0. Now, those asymptotes tell us a lot about limiting behavior. So if we looked at the red line, we can talk about the limit as x approaches 0, from the right, from the left, from both sides. We could also look along the horizontal axis, that green axis, and we could talk about, well, what happens as x gets sort of infinitely large, right? What happens as we go to the right forever? Well, it levels off at the x-axis at y equals 0, right? And we could talk about it from the other side as well. So this is all about limiting behavior. So we're going to consider taking that graph that you've drawn and finding the limit as x approaches 0 from the right. We could say that the limit doesn't exist because it's approaching an asymptote, and that would be correct. We could also say the limit's infinity. And by saying that the limit is infinity, more information about the function is conveyed and in fewer symbols. So I want to go back to this picture for a second, and then we'll talk about the vertical asymptote. So in other words, if we're approaching x equals 0 from the then we would sort of be traveling up the graph like this, because that moving right actually indicates on this particular graph, as I move right, I'm going up as well, going uphill, right? And while I can say it doesn't exist, and that's true, by saying that it equals infinity, that gives me a lot more information, because it tells me how the graph is changing as well, not just that it doesn't approach a specific numerical value. Do you see that? Because otherwise, if I just say doesn't exist, I don't know if the graph's going up forever or down forever, or maybe there's a jump in the graph, right? Maybe there's something else weird going on there. We don't have as much information, whereas if we say that it goes to infinity, that gives us some extra information about what's happening. So when that happens, when it goes to infinity or negative infinity, what we actually have happening is we have a vertical asymptote. And what you're seeing happen in these pieces of this lesson is algebra. So if you remember, the way we find a vertical asymptote is the first thing we have to do is we have to reduce whatever rational function we're working with so that we can cancel out any common factors. Have to reduce first. And then once you have the reduced fraction, you set your denominator equal to 0 and you solve. That's how you find the vertical asymptotes. Finding horizontal asymptotes sounds so much trickier because there's 3 different cases that can happen. The first case is if the degree of the numerator is greater than the degree of the denominator. So if you had like an x squared on top and you only had a single x on bottom. So if that happens, numerator degree is higher than the denominator degree, there's not a horizontal asymptote at all. If the degree of the denominator is bigger, that is, the numerator is less than the degree of the denominator, so you had something like x squared on top and x to the 5th on bottom, then you get a horizontal asymptote that's y equals 0. You get the x-axis. The third one is the one that's the most difficult to write out in a concise way, which is why it looks so wordy. If the degree on top and bottom are the same, then you look at a ratio of the leading coefficients. And let me just show you an example of that so that you can remember what that looks like. So let's say you had 3x minus 2 over 5x plus 1. The degree on the top and bottom are the same because those exponents match. They both have an exponent of 1. So then the horizontal asymptote is actually a ratio of the coefficients of those highest degree terms. So it'd be 3/5 here. It's so much easier to do it than it is to write out how to do this particular one. Isn't that how life is a lot of times? You just do it. It's easier to do it. Yeah, this one. So, all right, we're going to do an example then. Example number 1, determine all horizontal vertical asymptotes. Each vertical asymptote decide if the function value approaches infinity or negative infinity on either side. And we'll do that for the most part with a graph because we have the ability to do so. All right, so to start with, 3x squared plus 1 over x squared minus 2. Let's do vertical asymptote first, simply because I defined it first, not for any particular reason. But vertical asymptote, what am I supposed to do if I find my vertical asymptote? Say again. We're going to let the denominator equal 0. We actually have to do something before we do that, though. We check to make sure it doesn't reduce, or we reduce it if it can. So the denominator here actually factors. Does the numerator factor? It doesn't. So factoring the denominator for the purpose of reducing doesn't help. Now, it's going to be necessary in a moment anyway, so I'm going to go ahead and factor it. How will that denominator factor? Look good to everybody? Okay, and since the numerator doesn't factor, we don't get to reduce anything. So we checked to make sure it didn't reduce in our minds, right? We made sure that. So the next thing that we do, we'd set the denominator equal to 0. And I'll put the reduced denominator, that is the factored form, down because it's more helpful. So where is this denominator equal to 0? Okay, so it's at x equals 3 and x equals negative 1. So these are my two vertical asymptotes. Please make sure that you say x equals. Because if you don't say x equals, it's not an equation. It's just a number. And these are supposed to be equations of lines. And these are vertical lines, so they're x equals. So I have two vertical asymptotes here. Now we've got more to deal with on the vertical asymptotes in the directions, but we'll come back to that in a minute. So I'm going to skip a little bit of space, and then let's do the horizontal asymptote. So horizontal asymptote, which case am I in? Case 1, 2, or 3? This is case 3. And I'm going to jot that down just so that we all remember that we actually looked at this to make that decision. This is case 3. Why?
Is the degrees are the same?
The degrees are the same. What are the degrees?
The degrees are squared?
Yeah, they're both 2, right? I have a highest degree on top and highest degree on bottom, and they match. So what will my horizontal asymptote be? Yeah, it's going to be y equals, and it would be 3 over 1. So that's the y equals 3 that many of you said, right? So a horizontal line at y equals 3, that's the asymptote. All right, I have one more piece of information to do, and it's actually 4 pieces worth. So grab your calculator because you're going to need a picture of this to see what's happening. What we need is we need the limit as x approaches 3 from the left of the function. Okay, some of you, this is actually a good time to remind you of this. Some of you actually on your homework left out that function, like you would just say limit as x approaches 3 equals. Without the f of x next to it, it means nothing. It's kind of like saying, some of you, the equivalent would be saying square root equals 2. No, it doesn't, right? Square root has no meaning apart from what's underneath it. Limit has no meaning apart from what you're taking the limit value of either. So make sure as you're doing these that you're including this function value right here inside of or next to that limit. So I need to do the limit as x approaches 3 from the left. I need to do the limit as x approaches 3 from the right. I need to do the limit as x approaches negative 1 from the left. And the limit as x approaches negative 1 from the right. And your graph gives you a lot of that information. I don't have my calculator with me with my graph today, but did you guys get a graph? And do you see asymptotes on yours, Blaine?
Yes.
Excellent. So as you're looking at that graph, we're just going to go in the order I wrote them down, not because it's specific, but because it's already there. What is the limit as f of x approaches as x approaches 3 from the left? Does the graph shoot up or does it shoot down as you're getting close to x equals 3 from the left? Is it down? Here, let me do this. I'll draw it on here so I've got record of it. In theory. All right, let me put it over here.
Oh, x equals 3. Yeah.
Taylor, let me see your graph real quick. So the graph has a rough sketch of something like this. Okay, so it looks something like that on your screen. I make no claims that I got this perfect, but it roughly. And I'm left to assume from your screen that this is -1 and this is 3. My graph is definitely not drawn to scale, but. All right, so if I'm approaching 3 from the left, I'm over here. Is everybody with me on that? Okay, so is that approaching positive infinity or negative infinity? That's negative infinity. How about 3 from the right? Yeah, that one's shooting upwards. That's positive infinity. How about -1 from the left?
Positive infinity.
Yeah, this is this green piece right here. And -1 from the right? That's negative infinity. I think that graph helped us for us to see it together. Does that make sense? Okay. There is one other type of asymptote. It's called a slant asymptote. It happens in rational functions, which is the kind we're dealing with primarily in this section. And it happens in the case where the degree of the numerator is exactly 1 larger than the degree of the denominator. So if the degree of the numerator is larger than the degree of the denominator, there's not a horizontal asymptote. Okay? But in the case where it's exactly 1 larger, and then you get a slant asymptote. And you can find the equation of that asymptote by using long division. And I mean long division of polynomials, like in algebra. Okay? All right, so we're going to do an example of that. All right, so here we have a function x squared plus 1 over x minus 2. It says to determine all vertical and slant asymptotes. Okay, so vertical asymptotes. How do I determine vertical asymptotes? Only after I do what, though? Reduce. All right, so first of all, you have to look at it and say, does it reduce? And on this one, the answer is no, it doesn't. So then, once you've answered that question, then you've actually got it in reduced form. You can take the denominator and you set it equal to 0. What is the vertical asymptote?
X equals 2.
X equals 2. That one's easy, right? I didn't even have to factor that denominator, so that one was nice and clean. Now, the slant asymptote requires long division. Now, again, the slant asymptote only happens when the degree of the numerator is 1 more than the degree of the denominator. Is that the case here? Yes. The degree of my numerator is 2, because I've got x squared. The degree of the denominator is 1, because x does not have a visible power, so it's understood to be a power of 1. So I take my function and I use long division. So I put the x minus 2 on the outside, and I put the x squared plus 1 underneath the division bar. Now, I'm going to leave a space and put a 0x in here and then plus 1. Because there aren't any x's right now, I need a placeholder. It's kind of like when you have the number 101, you don't just write 1, 1, you actually leave a 0 for the tens place, right? Same thing here. All right, so the way that I ask myself this question is I say, what do I need to multiply x by to get x squared? X. So that goes in above this. And then I do the multiplication. X times x is x squared. What's x times -2? -2x, and this is the reason why I wanted that placeholder held, because now something's in that spot, that x spot. Now, what did you do in arithmetic back in 4th grade or thereabouts when you were doing long division after you sort of multiplied this? You subtracted. Now, the equivalent to subtraction is changing signs. So I'm going to change both signs because that's what subtraction is. So then we notice, oh, I've got a typo. Thank you. Yeah. All right, so you notice you've got the x squareds lined up. One's positive, one's negative, which means they add to 0, right? And then I've got the 2x underneath here, plus the 1, which I pull down. And I ask myself the same question. What do I have to multiply the x by on the outside to get the 2x that's now down here at the bottom? 2. So then I do 2 times x, which is 2x. 2 times -2 is Thank you, -4. And then I subtract, which is changing my signs. The two x's add to 0. The +1 and the +4 now actually become a +5. I know I'm done because this value 5 has a lesser degree than the x minus 2. That's when you know you're done. Is when the degree down here, it's called a degree 0 when there's not an x involved, is a lesser degree than what you're dividing by. So the answer then for my slant asymptote is actually y equals the value up here on top. And visibly what that means, if you were to look at this graph, is that you actually have the line x equal to 2, that on the ends of this graph, it's approaching that value. So it looks something like this. And this line right here is not drawn well at all. Pretending though, that's the line y equal to x plus 2. Use your imagination. Your graph will be much better on your calculator.